Okay, here we are, acid dissociation constant Ka. So here we've got the equilibrium of a weak acid interacting with water to make the oxonium ion and A minus. And we can put that into it's an equilibrium. Let's put it into Kc, products on top of reactants. But if you look, it doesn't quite work because water is a liquid. It's not the same state as everything else. And the concentration of water is constant, especially when everything's done in an aqueous reaction. It's 55.5 recurring moles per dm cubed. That's not going to change. And Kc is a constant, remember. So why don't we just bring this up over to this side to make Kc times H2O concentration. This is all one constant, and we call that Ka. So it becomes the acid dissociation constant. And we can sometimes we prefer just to simplify that H3O plus down to an H plus as well. So we've got Ka equals H plus over A minus times by HA. And this is the expression used. And you obviously substitute the acid and its conjugate base in there to suit for whatever one you have. So for example, top one here we have ethanoic acid. We've got Ka is simply H plus times by the ethanoate concentration divided by the concentration there. Okay, and the actual value comes out at 1.8 times 10 to the minus 5 at 298 Kelvin. Here's benzoic acid, and you've got the same thing. You take the two products, you put the product of them on top, and this goes here. Simple, really. And if if it moles per dm cubed cancels out moles per dm cubed, we just have 1 moles per dm cubed on top. The Ka unit is always moles per dm cubed. Simple enough. Now, what do these numbers tell you? Let's have a think. The bigger the Ka value, the more products you must have compared to reactants. So that means the more dissociation you have. So we can see here that benzoic acid has a higher Ka value than ethanoic acid. That must mean it's a stronger acid. But comparing these numbers, and they're times 10 to the minus something, can get a little bit messy, and so we have a method just to clean it up a bit. We use something called the pKa. The pKa is simply the minus log of the Ka. So that gets rid of the minus, gets rid of the minus number obviously, and the log gets rid of the 10 to the power. So for example, 1.8 times 10 to the minus 5 becomes 4.74. This number here becomes 4.2. And basically, the larger the Ka value, the stronger the acid. The smaller the pKa value, the stronger the acid. Okay, so think of the pK a little bit like pH. You think, a lower pH, stronger acid. Okay, pKa value, the lower it is, the stronger the acid. It's just easier to compare these two numbers than it is these two. So if you know which one's stronger, that's the one that's going to donate its H plus to the weak one. If you mix these two together, these two acids, you can actually make the acid behave like a base. This acid here would donate its H plus, and here it is over here after it's donated its H plus, and it's donated it to the ethanoic acid, and you can see there it is. It's become H2 plus. An extra H is joined onto the lone pair of the oxygen there. So I'll put an A here because this one's acting as an acid. I'll put a B here because this one's acting as a base. But when the reaction goes in reverse, it's the opposite way around. This one is acting as an acid because it will lose its H plus, and this one will be the base because it will regain the H plus. The numbers just show the pairs. A1 goes with B1. Those two are a conjugate acid-base pair. B2 goes with A2. They're a conjugate acid-base pair. So to know which one donates the H plus, you have to know either its Ka or its pKa values. And the stronger acid will donate the H plus.